Our first talk today is by Jason Raber. It's called Helikaon Linux Debugger, and I hope you enjoy it.
So anyways, my name's Jason Raber, and I'm a team lead for a reverse engineering team that we have in Dayton. And we do red teaming, which is evaluating, we've got some commercial companies that do protections. We have embedded customers as well that are now getting into the protecting their firmware and hardware protections. And so we evaluate that, and we'll tell them how to strengthen it. And so some of the work that actually we got even next month is with a customer that's got a Linux type protection. And so we developed a debugger to help us analyze and get around those types of protections. And also in evaluating malware and stuff, we find that while Linux, Linux is not immune to the malware and viruses. I think what happens is with malicious software, majority of them tend to focus on Windows, but Linux is an operating system that's fairly popular, and it does get malicious intent. And so what happens is what they want to do is protect their IP. In other words, just by the casual inspection, you can't understand what they're doing. So what they'll do is like packing and that type of stuff. But even after you get through the packing and start actually debugging it, they'll start catching you on some anti-debugging type tricks to cause you to maybe analyze code that you really are not interested in, like honeycode. Okay, and so like cost debuggers like GDB or IdaPro that works for Linux, like I said, these type of, basically the way like Ring 3 type debuggers like GDB work, these types of malwares will embed code in there to utilize these types of debugging measures that like GDB uses. And so they can check to see if a debugger is being used, and if so, like I said, crash out. And while it's interesting to kind of break those types of protections and understand really what it's doing, we generally want to do it pretty fast. So in doing that, I don't have to see every single one of them. Let me back up just a second here. So basically, I want to talk to you about what anti-debugging is, and then Helikaon and how it kind of works, show you a little bit of what the output would be, and then I'll go down into the nuts and bolts of really how I developed it and how it really works. And then this and that and some future work that I want to do. Okay. Okay, so like I was saying before with GDB and IdaPro, or they register with the OS. So essentially, like if you add an int3 and like say you want to debug something, which is the opcode is CC, and that causes a trap that will allow you to analyze a particular address and maybe some registers and that type of thing, or you can use hardware registers as well to look at those areas of memory. Well, again, those things are easily exploited, and so to keep you out of their IP or understanding what they're doing, they'll cause it to crash, or and some of the better stuff actually doesn't crash. It'll keep running and just run somewhere else. And then also in Linux, they use ptrace, which is a process trace, which is GDB uses. Again, you can put that bury that in your code in a number of places to catch if a debugger is being used. And so, with this, basically, Helikaon is a driver that I developed, and so it gives me certain access rights being done at that level. And what I've done with the Helikaon is actually rootkit my own system, which is okay since I own the system, and I'm not trying to, it's not like an anti-rootkit tool or anything like that, or detecting rootkits, but I'm actually rootkitting myself so that I can exploit certain things in the operating system to allow me to stealthily look at memory without being detected. Okay, so I can talk about that. Okay, so just kind of give you some ideas of some of the stuff that we've looked at, and on the malware side too, is they, these are just, like I said, just a small sample of what's really going on as far as exploits that they use trip you up if you're using, like I said, GDB or, I mean, even a hardware emulator or a kernel debugger is going to use, debug registers, which again can be caught. And if you set an address there, a common technique is to actually, push all the registers and then check to see if any of the DR registers are being used, and if so, then it will sometimes just clear them out and just keep going so that your breakpoint never hits. And you can see, like I said, there's timing checks and parent-child type debugging and looking in the process self-stat directory. And obviously, we've tried this on a lot of these different samples, and our debugger's not getting caught. Okay, so really, what is it doing? What am I trying to do with the driver? I mean, in the simplest sense, I want to analyze some area in code. So what I do from kernel land, I have a mechanism that lets me know that the software that I want to analyze has been loaded in memory. And so what I do is I reroute that code with a jump. It jumps to some sort of slack space, and then I can analyze, push the registers, and it allows me to manipulate the registers. Maybe I want to change a register or change memory. It allows me to do that, and I have a mechanism or a protocol that I let my driver know that I've hit my breakpoint and I'm interested in doing something interesting or analyzing some area of code. And again, all these, from the driver's perspective, all the injections are dynamic, and I replace them as soon as I'm done analyzing that code. In other words, like I said, I'm rerouting the actual instruction. And so I replace it back as soon as I'm done analyzing it. And so no types of checksums in that regard is getting caught. Let's see here. Okay, so to kind of give you an idea of just some real simple anti-debugging type stuff that can be done in Linux. You can see here I've got this function called foo that it doesn't do anything, it just prints out foo, but the idea is that maybe this function, I don't know, checks for some sort of key or gets a key or is some sort of a password or something. And the reverse engineer wants to analyze that area of code. He would put a breakpoint there using GDB and to analyze it. Well, in Windows too, they do this similar, is that they do these handlers that they set up. And you can see following down, I've got this handler that looks at a global variable and sets it to 0 if that exception gets caught within the process itself. So in other words, if a debugger is running and there's an exception, it gets thrown to the debugger. And so it doesn't get passed on to the program. And in those particular cases, you would see that the trace would not get set to 0. And then I've got another function called test trap, which again, I'm causing some sort of a trap or an interrupt, again, which gets passed to the debugger. And then looking down in the main, you can see that, that we register our handler right here, and then we actually cause the interrupt. Okay, and then obviously if there's no debugger being that's capturing that exception, it's going to be set to 0 because our own exception handler is going to catch it, and it's going to continue on and not print out that it's been detected. Like I said, you're not going to see this in malware where it's going to say debugger detected, although I have seen, believe it or not, some malware actually doing this very thing, is actually spitting out that there's been some sort of debugger running it, and it just crashes out, which is great for us because then we're able to trigger really fast on where that error was. And in another case where, like I said, you're looking for CCs, so we're dereferencing some memory of where that function is and looking at the opcode to see if there's a CC there, which again, if you apply the software breakpoint there. And then, of course, ptrace, if it returns anything other than 0, it's going to be detected. And so using DDD, which is a wrapper for GDB, you can see here I got up the function foo, and it's push EBP, and which is at 55. Put a little breakpoint there. And so when I actually run it, here you can see that I've got some sort of signal that happened, right, or a trap. And it tells me the line, which is kind of nice because then you can kind of go find that protection. But maybe there's 100 of these things scattered all over the place, and that's kind of like really annoying to try to continue to keep finding each one and knopping them or getting around them or scripting them out. So that's, again, why a custom debugger that doesn't fall under these same rules as other debuggers allows you to, like I say, quickly analyze code without being bothered with a lot of different protections. Anyways, when I hit continue, you can see now the printouts or the debuggers are detected for the signal, the CC, and the P trace. And I actually hit my breakpoint too. Okay, again, this is the disassembly of what the program looks like. And so what I'm going to do is in the Helikaon driver, I'm going to go ahead and add a breakpoint to this address, 80481D8. So kind of try to remember that address. It'll keep coming up. Okay, so just to kind of show you how you would install the driver. If you're not Linux heads, it's you use insmod, load the driver, then run the program, and then remove the driver. And you see here that in our example of the printouts of debugger detected, we're not seeing that with the Helikaon. And if you go down a little bit further, down in this area, you can actually see where from the kernel driver, I'm actually spitting out the address. Okay, so the breakpoint's been added. In other words, I'm interested, the process is up in memory. Go ahead and add the breakpoint. And then the breakpoint's hit at this address, which is the address I showed you before. And then I print out all the registers. Again, just for dynamic analysis type thing, you can now look at what the registers. And what's interesting too is when all this code's executing, it's all really down into the driver itself, so I can actually change the registers themselves, and I'll get into really what that all is. Okay, and some other interesting points too that I'll mention here and we'll come back to later is because we rootkit the system, we're redirecting all the syscalls to ourselves and to the Helikaon driver. So what's interesting there is that you can kind of actually mine the code first time without even running the driver to find all the return addresses. Because what I do is I print out all the return addresses for all the syscalls. That way it kind of gives me a toehold real quick into the virtual address of where the code is being executed. What's interesting is if there's some sort of JIT or encryption going, or even packing for that matter, when those syscalls actually gets executed, I'm going to get control of that. So interestingly enough, I can dereference that whole memory. In other words, dump it after it's been decrypted. And I don't have to sit and fight through keys or anything like that and trying to figure out how to brute force it. Okay. There are three things that you need for this driver to work. One is the breakpoint, which you can see right here, the BP1. And you can have as many as you want. But it's that same address, 80481D8. I need some sort of slack space where I'm going to put some handler code and a syscall address. So what I do is, like I said, I'll run the malware through. I'll go ahead and get all the different syscalls and get all their addresses, so I know exactly where they're being executed in the code. Okay, and so where I find one that I'm of interest, that happens very early, maybe like in startup code. If you disassemble a Linux compiled program, you're going to see that there's always some sort of bootloader code or startup code for CNIT and that type of stuff that happens early in the game. So you can use that guy. Okay, like I said, you can use the uname. And what's interesting too about the uname or anything in the startup code is that once execution actually has hit the syscall that you've hooked, all the code above it is really slack space at that point, right? Because it's never going to get executed again, not at least in startup code. Because the entry point has already happened and it's gone down a little bit. And for really what we're doing for our handler code, it's really, we only need around 20 bytes. So it's very, very small footprint. Okay, so what really happens in the Linux kernel when an interrupt happens, or these syscalls, right? So you see the int 80, that's a way of an interrupt that goes and notifies the kernel that execution is going to go down to the kernel and handle this syscall. Okay, so this is just the normal operation. And you see that we're right above the int 80. You've got to move EAX and then 7A, which is an identifier to let the kernel know what syscall it's actually using or going to call. Okay, so by hooking all the different syscalls, this picture's not exactly right, but what happens is there's still an int80, it still goes down to the kernel, not right directly to our driver. But in the end result is it does go to our driver before it really goes to the actual syscall of uname. Okay, and then we have a choice, we can actually execute it if we want to, modify the parameters, do whatever we want. In this particular case, we actually want to then inject a breakpoint or jump somewhere in the process, right? I'm not going to go into how rootkitting, Linux. It's not a very hard thing. You can ask Google, and he'll tell you all you need to know. But I kind of put up a little slide here just to kind of show you that, for those that are not familiar with it, there's this syscall table, and there's these indexes, and you see the uname here, for example. Okay, so what I'm doing is copying off a pointer address and saving it off. And then what I do is I've got a hooked one, and I'm going to replace it in the array so that, again, when that int80 happens, the kernel looks it up and says, okay, where do I call? It's looking up a pointer address to go make that call to that function. So now I'm saying, give it to me. Okay, now what's interesting here is, right, so we wrote these little macros that kind of tells us if a program's compiled statically or dynamically, what offset is the return address of the actual function call. As you can see right here, right, this call uname has a return address because every time there's a call, the return address gets pushed onto the stack. So we can write this little predicate right here, right, that says, if the return address of the uname call is, in this particular case, it's the 8048322, right? Go ahead and add a breakpoint. So what's nice is uname's getting called all the time, right? And as the kernel is swapping in and out of memory of different processes that are running and stuff, they're getting called, but as long as this predicate doesn't match with where we want to inject a jump, it'll just continue on its merry way. You can see right here, we're actually calling the original one and going on. Okay, so this is more for completeness. I kind of put up what are all the different tasks that happen in what type of order. But I decided to come up with a diagram that I think will help describe it a little bit better. As you can see here, we've got the different steps here, 1, 2, and 3, and 4, and all the way up to step 11. It's a little complicated, but now that we got it all put together and it works well, so you don't really have to worry about that. So we see that we've got the user mode here and then kernel mode. Okay, and this whole block really represents maybe the malware or the process that we're interested in analyzing. Okay, and so you got the startup code, and in startup code it calls uname. Like I said, it could be anything you want. It doesn't have to be uname, but it just depends on what type of boot up code they're using. And so this is the first step. There's an int80. It passes down into the kernel. The kernel does some things. In the end result, because I've got it hooked, I'll wind up getting to my hooked uname. Okay, so the second step that I want to do is I want to steal the bytes of where I want to inject the jump. Because eventually I want to replace those bytes so I can actually execute that instruction, right? So I steal the bytes, I store them off, and then I go ahead in the third step. I lost my mouse. Okay, the third step right here is I'm going to go ahead and add the breakpoint. So at compile or at runtime, I'll actually figure out where I need to jump, from this destination or this source address to the destination of where my slack space is going to be. Okay, and so then I want to go ahead and add the handler code. That's the fourth step, right? And so really the handler code is a way of now I push all the registers. So think of it this way. Let's back up a sec. As execution goes from uname and finally hits my breakpoint or my jump, it's going to jump to slack space. And so what do I want to do? What am I interested in, right? Because at that moment, before it was getting ready to execute that instruction, it's replaced by a jump. So everything's kind of live at that point, right? All the registers are live. So I push them all onto the stack, and I cause another interrupt to, in other words, notify my driver that something's happened, and now I'm interested in looking at the registers, changing the memory, changing the registers, etc. So what I do is I hook another syscall called, what is it called? I don't even think fdata sync. I don't even know what it does, and I don't care. Because again, I've got a predicate in there, and I'm just looking at whatever address, because at compile time I know if, the same thing I showed you in the uname, if you're looking at that predicate, you kind of know what's going on, if you've hit some interesting code that's in your handler. Okay. The other interesting thing that I do with the fdata sync is that it takes an unsigned integer. Okay, so you see where I'm pushing all the registers on the stack? Well, the very last thing that I do is I look at the register that it's using for its unsigned int, which is moved into EBX, and it's live all the way down, even after the context switch, getting down into the driver. So what I do is I move the stack pointer into EBX so that I know exactly where all the registers are, and so then I can muck with them and change them or whatever I want to do. So again, once you see here where this another int 80 happens, is execution's going right in here. Okay, so step 6 goes down. Now we get control back to our Helikaon driver. And then in this particular case, I can now, since I know exactly where the registers are, I can dereference that, the stack pointer at that location, and I have all the registers. I can print them out. Another interesting thing is I just leave them on the stack, and I can change them on the stack so that when I actually return back to slack space, I pop them all off. So effectively, I'm changing the registers, like I said, on the stack. And so when I pop them off and then jump back into the original code, I've effectively changed the registers. So anyways, after I print all those guys out, I want to eventually jump back to the original place that I wanted to analyze. So I have to replace those stolen bytes and then return back to slack space. Sends me up back to here, and then the last instruction for the slack space is to go ahead and jump where I originally had a breakpoint. And that's pretty much it. So after that point, I've kind of looked, and you saw, I think up above, right here, where the registers, and was able to see. In other words, an F data sync was hit, and so I print out the breakpoint address. And what I did too, this is kind of like what some of the output would look like from the driver. I actually broke it down a little bit to see step by step kind of what's happening, right? So again, just as a rehash, you see that the uname is called. Okay, so now I'm interested, and I've looked at this return address, 804832. This thing sucks. And then you see that this foo right here, the 55, I want to go ahead and inject a jump there, right? So I calculate it at runtime, and you see that the memory was 5989, which is right here. And then I dereference it again, and now it's an E9, which again is beginning opcodes for a jump. Then I found some area in slack space. For this particular example, I picked an area that was just a C runtime function that's never called. But again, you could use the slack space that's all above the call to uname. And you could see where the 5589, where the code originally was, and that I inject. And I've actually got it where it's just doing like a push D or something like that, where it pushes all the registers on there. But I did this for, more for the display of making it easier to understand. But basically, you can see where I push all the registers. Let's come actually over here, yeah. So the jump has now been executed, and you can see right here where the F data sync. So in other words, I've hit my jump, my rerouted code that jumps to my slack space, and then I cause another another interrupt down to the Helikaon driver, and so that I know that. And more importantly, like I said, I've moved ESP into EBX, and then the 94, like I said, is the identifier for the F data sync. Then the interrupt happens, and then, okay, so at that point, like I said, I can change the registers in memory, and then when I return back to slack space, you see that now I'm popping them all off, and then the last thing I do is jump to where my original breakpoint was, which in this case, like I said, IdaPro finished it for me and put foo in there, but it's where I replaced the stolen bytes. And okay, so I kind of mentioned this before, where the nice thing about looking at different syscalls and stuff is that maybe on file or whatever I can't see where because everything's packed or encrypted or whatever. But by rootkitting the system and getting all the syscalls, I can now see after it's been decrypted where all that stuff is unpacked and decrypted, so I can easily dump it now right from my driver. What the plain text or the code would be. And then if you wanted to loop, rather than this mechanism of cleaning up or replacing the stolen bytes, right after the second interrupt that I caused the F data sync, I could actually just leave the jump there, and down in my slack space, go ahead and put the instruction that I stole, and just execute it there if I wanted to as well. It just kind of depends on what scenario that you want to look at, whether it might be just looking for one or or if maybe the area that you want to see is inside some sort of a loop. I think with this type of mechanism too, I haven't done it or anything, but I could probably do like instruction tracing and just start off at the very beginning where the entry point starts, start rerouting every single instruction. So the idea is once I replace those stolen bytes, the next instruction I can look at and go ahead and inject a jump, which again will go down to the slack space and start the whole thing all over again. And so, again, this took about a week to put together, so it wasn't really very difficult to actually write the driver. And I just thought it was kind of neat how, exploiting the int 80 for, used in, like I said, for root kitting syscalls and stuff, using that to the advantage of actually creating a little bit of a debugger that will allow you to look at memory and get around all the problems with malware and stuff, like I said, exploiting the fact that the interrupt descriptor table handles the int3s or single steps or in the E flags. These types of things that debuggers have to operate under, which makes sense because the majority of code that people are analyzing is not malicious and exploiting those types of weaknesses in a debugger. It causes us as a red team and a reverse engineering team to, after you bang your head enough times looking at code that keeps thwarting you, and like I said, it's kind of fun for a while, but then it starts really getting annoying, so it kind of leverages itself to create your own debugger. And we have another debugger too that's also Linux too that we used, I don't know if you're familiar with QEMU, but we leveraged that and created a whole system emulation of Linux and Windows, and we can debug either one. The problem that I see with using that one, like it works on simple cases of malware and stuff, but if there's any kind of hardware component that's added to it, you have to emulate the hardware too, so it becomes cumbersome for doing really quick type stuff or analyzing quick stuff. So this kind of driver works out well for just getting a quick one-day look at something and understanding what it does without getting caught. Last thing too is I've got some ideas on actually, because the slack space is the only thing that's been bothering me. It's a small footprint. It's only about 20 bytes. For the handler code, I want to, ideally, after I've kind of analyzed some code, down in my driver, actually replace those stolen bytes, because I could steal those off too as well and then replace them. One thing I haven't tried, and the only idea I've got right now is when I'm actually down in the driver at the second interrupter, replace those stolen bytes and then possibly jump right from the kernel space right into user space. I don't know if you can do that or not. I haven't tried it. I know that you can't go from user space down into kernel space. In Linux, it doesn't like that. So, but I might be able to, from kernel space, jump right into user space. And since the stack could be a little bit weird because there's a lot of different calls that happen in the Linux OS to get you down into your actual driver, you could probably just, since you know the delta of where the original rerouted code was from when you push the stack pointer on, you could just subtract, or in this case, because it's high to low, you could add to the stack. In other words, pop everything off the stack from that original jump. But if anyone has a lot of Linux experience, I'd like to talk with them on that if they have any ideas. So, another thing I'd like to add eventually is maybe some sort of GUI front end type thing. Now, the way it works now, which is nice, is there's no kind of timing checks because it all runs at runtime. It's very, very fast, and so there's very little overhead that delta's, So even using different type of timing checks, we don't get caught. However, if I run some sort of front end where you have more of like a traditional debugger where it stops execution and then you've got a chance to analyze whatever the registers are and modify them right then and then say next or step into or whatever. That's the only kind of caveat that I'm seeing right now is that then I would lose that feature of timing checks and stuff. In some cases where, like I said, you're hooking the entire syscall table, so there's some calls that say different malware might make to check to see what the timing is and do another check later. Well, obviously, if you've hooked all those calls, you can modify those return, to make the delta much smaller. But there are also assembly instructions too that are not part of the syscall that will do timing checks, the checks for the timestamp counter. So that's it. So, yep. Any questions? Yes.
First, actually, exactly outstanding presentation. The was inspired by the Detours project, because when I looked at your site, it was looking at Detours on Windows with an additional loop in there. Is that correct?
Yes, we actually have, we've done some work in Detours as well. It's a Ring 3 type rootkit, I guess, rootkitting or at least redirecting syscalls or DLL type calls. And so, yeah, we do some Windows work as well. And so I was kind of, we've done, like I said, we've got Detours, we use that, and that kind of gave some inspiration on writing this one. Except what I don't want, like with Detours, for example, is it actually creates some trampoline space or slack space, which then is growing the size of the executable. Ultimately, I don't want to do that because I haven't seen it yet, but that's not to say that, different protections couldn't detect that you're actually increasing the slack space of the process. And if that were to happen, so I'm always trying to think a little bit ahead of those guys and how do I make it. So that's why I'm saying my real problem right now is figuring out how to clean up that slack space completely so it's oblivious. So I won't get caught by the checksums, right? Yes? Right, that's right. Absolutely. That's kind of like I said, that's where I'm kind of at right now is the whole slack space part thing, right? Because if I reroute every single instruction, then I'm not going to get caught by a checksum, right? However, again, that slack space is the part that's haunting me. It's a small footprint, but it is there. So you either find those checksums and nullify them, in other words, get rid of them, or I got to figure out a way to, from my driver land, go ahead and replace those stolen bytes, then go ahead and jump back into the process, right from kernel land. So I got to figure out that mechanism. I haven't had a chance to actually try it. But something I'm, yes.
Jumping back to user space from the kernel, I guess you don't want to do that unless you're begging for kernel exploits. Because, just jumping to user space code, first of all, you might fall into base faults.
Yes, I check that actually. Before I inject the jumps and all that type of stuff, I make sure that hasn't been swapped out. Or
User space code in ring 0. So, and you're basically just giving like complete access to the system, to the code that's actually running.
True.
Yeah, so yes, you might want to do that.
True, yes and no. I mean, in the scenarios that we run under, we have malware machines, and so we don't really care. Yeah, right. I mean, I'm not going into a system where everything's very sensitive, right? That's the great thing about being a reverse engineer and having your own lab, is that all the rules are broken, right? I've got complete access as it is, right? I have root, so I can kind of do what I want. Well, that's what I was talking about. Is I actually know, right, what the stack pointer is because I push that right. I move it into ABX, so I kind of know what it is, and so what I could do is do an add. And then that delta, which is effectively popping everything off the stack. So I kind of got that figured out. The hard part is, can you just actually do a physical jump right into user space? I don't know if you could do that. I haven't had a chance to test it.
Other question. So since you're basically changing a breakpoint into a jump,
Yes.
within your instruction tree, then you still have a kind of footprint. If there's any kind of checksum done on the binary, then you will detect it.
Well, actually, what I was, I guess, alluding to before is that if I reroute every single instruction, that's not the case.
Yeah, okay. But then, I mean, how is it better than just using okay, for instance, if you would use a breakpoint, and for instance, in the kernel, you could register in the breakpoint amplifier chain, and then look for the specific instructions where you added the breakpoints, and not simply use breakpoints. It would have the advantage of, since the breakpoint is only one mode, then you can breakpoint on any instruction. I wonder how you deal with instructions smaller
Well, like I said, I don't really care. Like if it's a push, which is 1 byte, push EBP, and then followed by some other instruction stuff, I'm just copying 5 bytes off and replace it with a jump. So, eventually I'm going to hit that jump, right? When that happens, it'll go to slack space, which I have the stolen bytes. The first thing that I do after the jump goes to slack space, when I get the interrupt to myself, I replace those stolen bytes, so it doesn't matter what the size is, right? Because it's going to put the 55 right back, followed by whatever instructions are after it. So then when I actually jump back from slack space, when I hit the push,
My question is basically, why do you need this slack space? If you use the standard breakpoint, then there's no need of slack space at all.
I'm not sure I follow. I mean, using the breakpoint is what I'm trying to get around.
If you insert a breakpoint instead of a jump, then
Yes.
you go right into the kernel. And if you deal with that within the kernel and go back directly to user space, all the techniques, techniques you talked about will be, won't get
Are you talking about creating a different type of interrupt and registering in it? Because one thing you could do is you could create your own opcode, right? And then just hook the IDD table and add your own, and that's yet another method you could do, right? And so the checks that make, looks for CCs and hardware registers and those types of stuff, that's not going to affect you either, right? Because, that's something also that I haven't been considering and thinking about actually doing.
check for CC and stuff, could check for jumps that you've added also. It's just that you're adding a new technique that people will also add.
Sure. I don't think that the malware authors are going to run out there and start worrying about me. So, yeah, that would be flattering, but yes.
What do you do with the jump technique with an instruction at the end of the memory phase, whether it's emergency or 5 byte or 2 byte jump?
Well, I don't do a 2 byte, I do a 5 byte, and so.
Yeah, but if you're at the end of the phase where you only have 1 byte left, what do you do?
I guess I don't follow. Oh, I see. Yes, that's a good question. I guess I don't do anything. In that particular case, a lot of the times when I'm analyzing code, I guess that's the other thing I didn't get a real chance to say. When I look at code, I use IDAPRO mostly for like static analysis and getting dumps, and I think the better you get at reverse engineering, the less you need to rely on dynamic. However, there's always some points in the code that you really do need to see what's in those registers. And so a lot of times when I'm breaking something or looking at something, I will identify quickly through static analysis some key points maybe that I want to analyze. And so, it might come down to me adding 3 breakpoints total to break something. You know what I mean? That's true. Fair enough. Yep. Well, the other thought that I had with the rerouting every single instruction, like a data access type breakpoint, which is I'm rerouting them all, and I'm not really looking at them. All I'm doing is looking at all the registers and stuff to see if the instruction pointer might be getting close to that execution and then cause a break. So, yes?
Well, if you mentioned reroute every instruction, do you deal with non-relocatable instructions, such as, let's say, offset-based jumps or anything that, is impacted by the instruction pointer?
But I'm not executing it from the slack space, right? I'm going to replace it and then jump to the place that I originally had to jump. See what I'm saying? I'm rerouting the instruction before it has a chance to execute or intercepting it.
But then, eventually, you want to execute it.
Sure, but it'll be right back to where it was.
Or do you execute that?
I execute it from the place that it originally was.
Okay, so you don't support root threads then?
Guess not. Yeah, questions? Yeah, well, remember I said in the very beginning, I need 3 different things, right? I need the breakpoint, I need to know where you want to analyze, I need to know some sort of slack space, and I need to get some sort of a toe or... Yes, you do. But again, this is not like a debugger that's it's sold, and yeah, it's something I use in the lab that doesn't take me long to compile it, right? Resetting it after I jump. Say that again? Yes? Well, I was saying, here, right, if you wanted to do this is a little bit more complicated because now I have to have a little bit of a disassembler because I could just execute the code from my slack space if I wanted to be in some sort of a loop, right? So long as, and then if there is some sort of relocation issues of relative type addresses, I'd have to recalculate that, right? But if it's a simple instruction, and I can look at that very easily, right? Is it a move EAX, comma EBX? Well, I don't care where I execute that from, right? But if it's something like a push of, some constant or something, then I have to recalculate where that might be. Yes, it actually does, because like I said, I need the slack space. Like I said, there has to be a little bit of redesign because I really want to get rid of that slack space. Then my footprint, or at least getting caught by checksums, would be gone. So, but yeah, right now, yes, it does support multiple. But what I can't do, right, is I can't have a breakpoint, on a push because I'm stealing the 5 bytes. So I can't put a breakpoint right directly under that. Does that make sense? So I have to make sure that there's enough space in between those guys to inject another jump. So, yes. Say again? I'm working on that. Is the source code available, open source? And I'm working on that right now. So I would say contact me. I have my contact information. Might be able to give it out. We have done that in the past, so because we don't sell tools, we're more of a service base. We, analyze your different types of protections or software and give you quick results back. So, any other questions? Okay.